Alright, today's lesson is going to be about this thing we call specific heat. As we continue on our discussion about energy and about energy transfer, there's this concept called specific heat. That's what we're going to talk about today. Now, this is a concept that you're already familiar with, even if you haven't put a name to it. So let's go ahead and take a hypothetical situation. Let's say that you've got a bar of gold and you have a glass of water. They're both starting at the same temperature. Now, if you leave them both in the sun for about 15 minutes, what's going to be the difference between them? Okay, you've got this bar of gold, you've got this glass of water, leave them in the sun for about 15 minutes, what's going to be the difference between them? And which one would you rather touch? Okay, would you rather touch the bar of gold that's been sitting out in the sun for 15 minutes, or would you rather hold a glass of water? Now, your answer to those questions deals with this, like I said, this idea of what we call specific heat. Now, again, you might not have been able to put a name to it, but you already kind of understand, okay? Some substances heat up easier than others, right? Probably most of you chose the glass of water. I would rather hold a glass of water at the end of 15 minutes than the bar of gold, because the bar of gold is going to be hot and the glass of water is not. I mean, it might be a little bit warm, but comparatively, it's one's going to be really, really hot. You don't want to be touching it. And the other one, might be a little warm, but it's fine, okay? The reason is, again, this idea called specific heat. Some things heat up easier than others. That's what we call specific heat, okay? It's how easy or hard is it to change the temperature of something, right? We could heat it up, we can cool it down, but changing the temperature, some things are easier than others to change. Now, if we want to use a technical definition of specific things, the specific heat is the amount of heat or the amount of energy needed to raise or lower the temperature of 1 gram of a substance by 1 degree Celsius. Now, that's the very specific technical definition. The actual, what we're actually doing here is saying how easy is it or how hard is it to change the temperature of your object, whatever it is, whatever your substance is. The higher the specific heat, the more energy it takes to change the temperature. Remember, heat is a transfer of energy from one thing to another because there are different temperatures. Well, how much heat can my object absorb before the temperature starts to change? That's what we're talking about with specific heat. The higher the number, the harder it is, the more energy it takes to change the temperature. Either absorbing it to increase the temperature or releasing it to decrease the temperature. So let's look at some objects, some substances that you might be familiar with, and we'll compare their specific heats. So we have aluminum, copper, gold, silver, ethanol or alcohol, and liquid water. Okay? Now, I will tell you right now, water has, or any substance has different specific heats depending on the state of matter. So if we look at solid water or ice and liquid water and gaseous water or steam, they have different specific heats. So you have to specify this is liquid water. Very, very, very important. Okay, so we've got our liquid water. Now, which of these requires the most heat in order to change the temperature? Looking at our 6 options here, which of these is going to require the most heat in order to change the temperature? And of course, the answer is water, right? It has a much bigger specific heat compared to everything else. Okay. Now, we've got some pretty funky units here for our specific heat. I wouldn't worry too much about them. We just need to have these funky units here for specific heat in order to make the math work that we'll talk about in a minute. So water's going to require the most amount of heat in order to change the temperature. Which of these is going to require the least amount of heat? Now, if you look here, the one that's going to require the least amount of heat is the one with the smallest number, which is right here, gold. Much, much smaller than water, okay? Even smaller than copper and aluminum, okay? Which means that gold does not require a lot of heat either coming in to increase the temperature or going out to decrease the temperature. That temperature is going to change fairly easily. If we look at another example here, let's say here's some more. We've got iron, we've got sand, wood, and again liquid water. Again, you have to specify the state of matter. So this is going to be solid iron, solid sand. There's no such thing as non-solid wood, but again, liquid water. So let's say we've got this situation here, right? So we've got metal cooking pans, typically have a wooden handle, okay? Why? Why would you want a metal cooking pan but a wood handle? Okay, now why would you want that? Now you want a metal cooking pan because you want it to heat up fairly quickly, right? If I put that on my stove or I put it over a fire, I don't want a lot of that heat to be absorbed and my pan not get hot. So I want something with fairly low specific heat, right? Here's iron, 0.45, fairly low. If you remember from the slide before, let me go back. Okay, even copper and aluminum pans, right? Even lower specific heats, okay? So that's going to heat up fairly quickly. Come on. There we go. But why would we want a wood handle instead of a metal handle? Well, if I'm going to grab this pan, I don't want it to heat up very quickly, right? I don't want the handles to heat up. I just want the pan to heat up. So when I go to grab it, when I go to move it, it's not very hot, right? Because it requires more energy to get the handle hot than the pan itself, okay? Now let's say that you go to the beach with your sister or you go to the beach with your brother, okay? Why is the sand always so much hotter than the water, right? You go to the beach and you walk across the sand and it's burning your feet. But you go to the water, it's nice and cool, even sometimes cold, right, compared to the sand. Why? Why is the sand so much hotter than the water? Well, of course, the answer, because that's what we're talking about today, is the specific heat. Sand has a much lower specific heat than water does, meaning it requires less energy to heat it up. So if I give them the same amount of energy, right, the same energy coming from the sun, the sand temperature is going to change a lot more than the water temperature is. So sand, comparatively to water, much lower specific heat, which is why the sand is going to get hot, but the water is not going to get as hot. So we've talked about the specific heat idea. We've talked about, last time we talked about measuring heat. Now we're actually going to have to calculate how much heat, how much energy is transferring from one object to the next. So let's start by thinking about what factors affect how much heat is needed. Okay, in order to change something, the temperature, right? If I'm going to increase the temperature, how much heat do I have to add? If I'm going to decrease the temperature, how much heat am I going to have to take away? What are the different things that can affect that? Well, the one we just talked about was specific heat, right? The specific heat of the object or the substance, whatever it is going to affect how much energy we need to put in or how much energy we have to take out, okay? Now, something else that you might have already known but haven't thought about is how big your object is, how much stuff you have, right? If I've got a small swimming pool, like a little kiddie pool, that's going to heat up a lot faster than a large pool, right? Or the ocean even, okay? So the mass of the substance, the mass of the object that we're trying to change the temperature, how much you have is going to make a huge effect on how much energy you need. Also, how much you want to change the temperature is going to affect how much heat you need. okay? If I want to change the temperature 1 degree, I just need a little bit. If I want to change it 100 degrees, I'm going to need much, much more energy, okay? Now, if I take all of these ideas, right, I take the specific heat, and I take the mass, and I take how much I'm going to change the temperature, I get this equation here. Remember, Q is my symbol for heat, okay? How much heat is needed? Well, I'm just going to take the mass, I'm going to multiply by my specific heat, and I'm going to multiply by my change in temperature. My temperature goes up, I have to add heat. My temperature goes down, I've got to take heat away. So this is the equation that we're going to use, and we're going to go through a couple of examples in a minute. It's very, very, very important before we move on to the examples that you remember this. This equation can only be used if our substance does not go through a phase change, right? If I have liquid water and I'm heating up the liquid water, it cannot boil. As soon as it starts boiling, this equation does not work. It cannot go through a phase change. Or if I go the other way, if I have liquid water and I'm trying to cool it down, as soon as it starts to freeze, I can't use this equation anymore. There will be another one that we'll talk about in a future video, but this equation can only be used when something is not going through a phase change, when it's staying in the same state of matter, either solid, liquid, or gas. As soon as we start changing phase, this equation doesn't work. All right, so that's the lesson for today. I'll be looking for the second video that will take you through some practice problems, some practice questions. If you have any issues, if you have questions, comments, concerns, please let me know. Drop them down in the comment section. Send me an email, and I will talk to you guys later. Bye.